In this video, we talk about another way to combine two functions, and that is the composition of functions. When we compose two functions, we substitute one function into another function. I have this little image on the screen where I'm talking about an input value of x, and I substitute that value x into a function g, so I get this output value g of x, which then I can substitute into a function f, which becomes f of the expression g of x. And so that notation or that operation is what we call composition of functions. Let me define it in more explicit terms. So to define the composition of functions, if f and g are functions, then f composed with g, which we read as f of g, is defined as f of g of x is equal to f and then in parentheses g of x. So that is, we are evaluating the function f at this other function g of x. So the input is now a function g of x, and that's being input into this other function f. Now please note the difference between the notation for composition and multiplication of functions. Composition uses this open circle or open dot to denote composition. If you see in parentheses f with a closed dot g of x, that is multiplication f of x times g of x. But this open circle denotes composition. The domain of f of g is a set of real numbers x in the domain of g such that g of x is in the domain of f. So that is, we have to start with a set of numbers that make sense in our inner function, and then we have to end with numbers that make sense in the outer function. And I'll explain that as we go through with some explicit examples. So let's look at this. We have f of x is equal to 5x minus 2, and g of x is equal to 3x plus 1. We want to find the requested information. In part A, that is to find f of g of x and state its domain. So we first want to rewrite f of g of x with our function notation. And this means to do f of, and I'm going to put this in parentheses in a different color. In parentheses I have g of x. So this is f, and then in parentheses g of x. So now we're just going to keep substituting. This means to do f of, and in place of g, I'm going to write what g of x is, which is 3x plus 1. So this notation is telling me to do f of the expression 3x plus 1. Well, to do f of anything, I've got to go to my function f, which is 5x minus 2. But f of anything then is 5 times whatever it is I'm plugging in minus 2. Well, in this case, I'm plugging in 3x plus 1. So do you see how we plugged the function g into the function f in place of x? And then when we simplify, we get 15x plus 5 after distributing minus 2, or 15x plus 3. Now the domain, we have to make sure that the numbers that we plug into the function are valid, so we look at the inside function. Are there any restrictions on the domain of g? It's not. There's not, because it's a linear function, so we know the domain of g is all real numbers. Are there any restrictions on the final function? And there's not. So we would say then that the domain of f composed with g is all real numbers, negative infinity to infinity. So we have to exclude what doesn't work on the inside function and exclude what doesn't work on the final function to get our domain of the composition function. Now we want to find g composed with f of x and state its domain. So let me write these two functions. F of x is 5x minus 2. And g of x is 3x plus 1. So now we want to find g composed with f of x. So g of f of x. Well, this is equal to, by definition, g of f of x. This is g of, well, now we put what f of x is, which is 5x minus 2. And so this time we're plugging the function f into the function g. So g of anything is to do 3 times whatever it is I'm plugging in plus 1. Again, I'm plugging in 5x minus 2. And when we distribute, we get 15x minus 6 plus 1, or 15x minus 5. And notice that this is not the same as the other composition. So the order in which you plug in does matter. Now what about the domain of the composition? Domain of g composed with f. We look at, are there any restrictions on the inner function? And there's not. It's a linear function, so there's no restrictions. Are there any restrictions on what we can plug into 15x minus 5? And there's not. It also is a linear function. So the domain is negative infinity to infinity. Now what if we wanted to find f composed with g of 4? F composed with g of 4 means to do f of g of 4. So we could do this with working with the 2 individual functions. We can also do it working with the composite function, and I'll show you that in just a moment. So let's recall, what were our 2 functions? F of x is 5x minus 2, and g of x is 3x plus 1. So one way that I could do this problem is I could figure out what g of 4 is. And so if we think about what is g of 4, g of 4 means to plug 4 into the function g in place of x. So that would actually be 3 times 4 plus 1, which is f of, well, 3 times 4 is 12 plus 1 is 13. So f of 13 would be, now we plug 13 in place of x into the function f, so this would be 5 times 13 minus 2. And when we simplify that, what is that, 65 minus 2, or 63. Now another way to do that is to think about, well, what did we find for our composite function, f composed with g of x? And if you recall, f composed with g of x was 15x plus 3. So we could find the composition of the 2 functions and now evaluate that when x is 4. So f composed with g of 4 would be 15 times 4 plus 3, or 60 plus 3, which is 63. So either way will work. And then what about g composed with f of 4? In a similar fashion, we could find g of f of 4. And f of 4 is, plug 4 in place of x into the function f's to be 5 times 4 minus 2. So let's think about this. Would be g of, what, 20 minus 2, or 18. And to find g of 18, we would do 3 times the 18 plus 1. Which is 54 plus 1, or 55. In a similar fashion, we could have just found the composite function g composed with f of x, which we did on the previous slide, was 15x minus 5. And so g composed with f of 4 would be 15 times 4 minus 5, or 60 minus 5, which is 55. So either way works. Now let's look at another example. We have f of x is equal to 2x minus 3, and g of x is equal to x plus 3 divided by 2. And we want to find the compositions f composed with g of x and g composed with f of x. So f composed with g of x is equal to f of g of x. And so I'm going to write this in 2 steps. Let's see. In blue, I'm putting in my function g of x. G of x is x plus 3 divided by 2. So to find f of anything, I go to my function f, which is 2 times whatever I'm plugging in minus 3. So what am I plugging in? I'm plugging in x plus 3 divided by 2. Right, so again, my function g goes into the function f. Simplifying this, well, 2 times x plus 3 divided by 2 is just simply x plus 3 minus 3, and that is equal to x. And then if we do g composed with f of x, we get g of f of x which is equivalent to g of 2x minus 3. So to find g of anything, we will replace x with whatever we're plugging in. Then we have plus 3 divided by 2. So we're plugging in the 2x minus 3. So again, here we're plugging in the function f into the function g. So 2x minus 3 plus 3 is just simply 2x and divided by 2, which is just x. And we'll learn about this in section 18 when the composition of two functions in both directions gives us x. Then those two functions are called inverse functions. And then one other problem here we have f of x is equal to the square root of x plus 3, and g of x is equal to x squared. We want to find the compositions and state their domains. So we have f composed with g of x, which is equal to f of g of x. I'm going to write out some things and then I'll go back and change my color. So then I'll substitute what g of x is. And remember, to do f of anything, we're going to plug into the square root function. Whatever we're plugging in goes in place of x, and then plus 3 inside the square root. So let's look at that. I'm going to go back and write this as f of g of x in blue, which is f of, now what is g of x? That's x squared. So plugging in x squared into the function f, we get the square root of x squared plus 3. Now we have to state the domain of that. So the domain of f composed with g, we have to think about, are there any restrictions on the inside function? There are no restrictions on x squared. That is a polynomial function that is defined for all real numbers. Then we have to think about, are there any restrictions on the final function? That is the square root of x squared plus 3. But remember, the square root is an imaginary number when the inside number is negative. So think about this. This would say that x squared plus 3 has to be greater than or equal to 0. In other words, x squared has to be greater than or equal to negative 3. But this is always true when we square any number. It's going to be 0 or positive. It will always be greater than negative 3. So there are no restrictions on what x will be to satisfy that inequality. So the domain is all real numbers. Now if we look at g composed with f of x, I'm going to write some statements here. So that's g of f of x. And then we'll go back and look at what f of x is to substitute in. And then g of anything is whatever I'm plugging in, and I square it. So let's look at this here. So g of f of x, and that is g of the square root of x plus 3, which is the square root of x plus 3 quantity squared. And when we square that, we just get x plus 3. But the domain of g composed with f now, this is where this problem is very different because we have to look at the inside function. Are there restrictions on what we can plug in for x? And there are, because the square root of x plus 3 is not defined for every real number. In fact, for the inner function, x plus 3 has to be greater than or equal to 0, or x has to be greater than or equal to negative 3. There are no restrictions on the final function, so there's nothing else to consider, but the domain then of this composition would be bracket negative 3 to infinity. At f of x equal 1 divided by x plus 4, and g of x is equal to 4 divided by x, and we want to find the composition f of g and state its domain. So f composed with g of x is equal to f, and then we're going to put the parentheses and whatever g of x is. So this is f of g of x, which is f of 4 divided by x. Well, f of anything is 1 divided by whatever I'm plugging in plus 4. And I'm plugging in 4 divided by x in place of x. So to simplify this is a complex fraction. I can multiply the numerator and denominator by the LCD, which is x. So I'm going to multiply my numerator by x and my denominator by x. And this gives me x divided by, well, x times 4 over x is just 4. And then 4 times x would be 4x. So x divided by 4 plus 4x. Now my domain, I have to think about what are the restrictions on the inside function. Well, 4 divided by x, we can't divide by 0, so x cannot be 0. And then the restrictions on our final function. We again have a rational function, so my denominator can't be 0, so 4 plus 4x cannot be 0. If we subtract 4, 4x cannot equal negative 4. And then we can divide by 4, so x cannot be negative 1. So my domain of f composed with g is a set of all real numbers except for 0 and negative 1. So if you need to think about a number line, place negative 1 and 0 in order. We have to exclude both of those, so that's negative infinity to negative 1 with the parentheses, union, parentheses negative 1 to 0, union 0 to infinity.